Our topic for today is transients in RC circuits and RL circuits. So this is resistor and capacitor circuits, resistor and inductor circuits. So we're talking about their transient behavior, the relation between the current and the voltage in both circuits. So let's talk about capacitor first. Capacitor. What is a capacitor? Capacitor is an electrical device used to store electrical energy. So we use our capacitor to store electrical energy. So it's an electrical device also, just like your resistor. Your resistor is an electrical device, a component in electronics. We used to store what? Electrical energy. So our capacitors are extensively used in electrical and electronic circuits. So we use our capacitor in electrical and electronic circuits. For example, capacitors are used to smooth AC output. So if you want to smooth your AC output, use capacitor. So let's draw our full wave rectifier, or let's use half wave rectifier. This is your AC connected to a step down transformer. Then your AC your rectifier. Let's draw our full wave. Let's use full wave rectifier. This, your diode connected in this direction. This is another diode. Then another diode connected here. Then another diode connected here. So these diodes are connected together. So then this is connected to it. The output is taken from here. Now this output can only be smoothened by what? By a capacitor. So this output is smoothened by what? By a capacitor before going to your what? To your load. So that's the one of the function of capacitor in rectifier. They are also used in telecommunication equipment such as radio receiver for tuning the frequency. So when you are tuning your frequency, is a function of the capacitor. They are used in your time delay circuits. Remember I'm talking about flip-flops in your digital circuits. In electrical filters, so we use them in electrical filters. We are talking about your band pass, your high pass, low pass filters. We use capacitor there. In oscillator circuits and magnetic resonance imaging, MRI, we use them there. In medical body scanner, to name but a few practical applications. I use them in many applications. These are the different type of capacitor you have: ceramics, electrolytic capacitor, different type of capacitors. So capacitor, every system of electrical conductor possesses capacitor. So every electrical conductor has what? Has capacitor. For example, there's capacitance between the conductors of overhead transmission. So if you have your transmission line, let's assume this is a transmission line. So between this line, there's capacitance there. There's capacitance between this line. That's what it's trying to talk about. So your overhead transmission line, there's capacitance. So for example, there's a capacitance between the conductors of overhead transmission line, and also line between the wire of a telephone cable. So your telephone cable too, there are standing wires and so on. There's capacitor between them. So in this case of transmission line, this capacitor is undesirable. We don't need them, but we have to accept them because there's nothing we can do about it. But we have to minimize it and compensate for it. So you have to find a way of minimizing this or compensate for it. There are other situations whereby this capacitance is a desirable property. In some cases, they are desirable. Devices specially constructed to possess capacitance are called capacitor. So things that can possess capacitance, we call them what? Capacitor or condenser. So sometimes we can call capacitor what? Condensers. This is what we used to call them before, but now we call them what? Capacitor. In the simplest form, a capacitor consists of two plates. So you have two parallel plates. Okay, let me draw it. So you have two plates. This is a capacitor, two plates, and they are separated by what? A dielectric material. a dielectric material. So it is a dielectric material is placed in between them. What is dielectric? Dielectric material are insulating material or a very poor conductor of electric current. They are poor conductor of electric current, so we place them in between them. A capacitor has the ability to store a quantity of static electricity, so they store electricity as we said earlier. The symbols for a fixed capacitor and variable capacitor is used in electrical diagram as shown below. So this is your fixed capacitor. When you have a capacitor in this format, so it's fixed, and when you have it like this, it's a variable capacitor. Just like if you have your resistor, this is a fixed resistor. So for your variable resistor, this is a variable resistor. So this is your fixed capacitor and this is your variable capacitor. Now let's talk about capacitance. Static electric field arises from electric charges. Electric field lines beginning and ending on electric charge lines. Thus, the presence of a field indicates the presence of positive and negative charges on the two plates of the figure below. So now, this is a capacitor, two parallel plates, plate 1, plate 2. This is the difference between the two parallel plates, G. Then the electric field produced by this capacitor due to this voltage is given as what? E, which equals to what? The voltage divided by the distance between the plates. So that means your V is equals to what? ED. So whereby this your E is the electric field in volts per meter or Newton per coulombs. So the unit of electric field is what? Volt per meter or Newton per coulombs. Your V is the potential difference, the battery voltage, and the unit is what? Voltage is in volts. Your D is the distance between the what? The distance between the two parallel plates. So and the unit is what? Meter. The capacitance of the plates of the parallel plate is given as, so the capacitance of this capacitor is given as what? C equals to Q over V, where your C is what? The capacitance of the capacitor. Your Q is what? The charge on the capacitor. This plate, one of the plates will have a positive charge and the other will have a negative charge, and V is the potential difference. So the unit for capacitance is what? Farad. The unit for capacitance is what? Farad. But we used to use microfarad, and what was micro? That's 10 to the minus 6. Or we use picofarad. This is microfarad or picofarad. Pico is 10 to the minus 12. So you know that 1 picofarad is equals to what? 10 to the minus 12 farad. Now the charge on the capacitor, is given as what? Your Q equals to what? IT, whereby the current flowing into the capacitor and the time the current is to flow. That means your Q equals to what? IT. That's the charge on the capacitor. The capacitance of a parallel plate capacitor. So you have a parallel plate capacitor. So you want to calculate the capacitance of a parallel plate capacitor, just the way you calculated the resistance of a wire. So now for your parallel plate capacitor, the capacitance C is equals to what? Epsilon A over D, whereby your C is the capacitance of the capacitor. Your epsilon is given as what? Is a constant, which is epsilon naught, epsilon R. You'll be given the value for every material, epsilon naught and epsilon R. What's the A? The A is the area of the plates, one of the plates. So if you are given a rectangular plate, that's length times breadth. And what's the D? That's distance between the two plates, the distance between the plates. So that means your capacitance is what? Epsilon A over D, where C is what? C is capacitance. Capacitance. Your E naught is epsilon naught and is a constant, which is 4 pi times 10 to the minus 7. Your epsilon R will be given for the material. So your epsilon R will be given, your epsilon R is known as what? Relative permeability. Relative permeability. To be given. So this is formula to calculate the capacitance of a parallel plate capacitor. But if you have n parallel plate capacitor, this is for 2 parallel plate capacitor. So if you have n parallel plates, the capacitor is calculated using this formula. Same formula, your C, which equals to what? Epsilon naught, epsilon r, A, then divided by D. But if you are given n parallel capacitor, that means you are going to multiply by the number of parallel plate capacitor minus 1. So as me are given 3 parallel plate capacitor, it will be 3 minus 1. It's because in this case we are given 2. That means your n is what? 2. So that will be 2 minus 1. So that means I'm going to have C to be equals to what? Epsilon naught, epsilon r, A over D. Then what? 2 minus 1. What's 2 minus 1? That's 1. That's times 1. We should give you back this. So let's solve the first example. Example 1. Example 1. The dielectric thickness between the parallel plate capacitor is 0.5 centimeter. So you have a parallel plate capacitor, you have this. Let's assume this is a parallel plate capacitor. There's a dielectric material in between, which is 0.5 centimeter, and its relative permeability is 3. So that means your ER, your relative permeability is what? 3. So that means the distance between this material is what? Is 0.5. Why is it 0.5? Because we are told that the thickness of the dielectric material is what? Is 0.5. And I told you that dielectric material is between a parallel plate capacitor. That means this is telling you that the distance between this capacitor is what? 0.5. That means the distance D is what? 0.5 centimeter. 0.5 centimeter. If you convert that, you're going to have 0.5 times 10 per minus 2 meter, because we know that our centi is what? 10 per minus 2. The capacitor consists of a rectangular plate, so we are told that it's a rectangular plate of dimension 10 centimeter by 15 centimeter. So the dimension of the rectangle is what? So the rectangle is what? 10 centimeter by 15 centimeter. So we need to calculate the area of the plate. And what's the formula for area of a rectangle? The formula for area of a rectangle is what? Length times breadth, which equals to what? 10 times 15. And what's 10 times 15? That is 150 centimeter. And notice it is in centimeter, that is 150 centimeter square. So convert the centimeter square to meter. So you're going to have what? Your 1 centimeter square, as we always say, is what? 10 per minus 4. 10 per minus 4 meter square. So we convert this, we're going to have 150 times 10 per minus 4 times 10 per minus 4 meter square. Then we are told that the electric field strength of the electric material is found to be 30 per centimeter. Sorry, this means 30 volts per centimeter. So that means the electric field E is what? 30 volts per centimeter. So convert this per centimeter to per meter. So that your 1 centimeter, we know it, your 100 centimeter is what? 1 meter. Is 1 meter. So let's convert this. I'm going to have 30 volts per centimeter times 100 centimeter divided by 1 meter. 1 meter. So this centimeter will cancel this centimeter. So 30 times 100 is what? That will give us 3000 volts per meter. So that's our electric field, 3000 volts per meter. And has to determine the capacitance and the total charge on each plate. So you have to calculate what? You have to calculate. Let's calculate the capacitance and the total charge Q on each plate. So we know that our capacitance C is what? Epsilon naught epsilon r A over D. That's formula for our capacitance. And what's our epsilon naught? is a constant. I told you epsilon naught is a constant, which is what? 4 pi times 10 per minus 7 Henry per meter. That's our epsilon naught. So, and our ER, relative permeability, is given as what? 3. So the relative permittivity is what? 3. So they are going to have epsilon naught, which is what? 4 pi times 10 per minus 7 times, what's our ER? That's 3 times 3 times the area. What's the area? The area is 150 times 10 per minus 4. The area of the plate, 150 times 10 per minus 4. Then divided by the distance between the capacitor. What's the distance? That's 0.5 centimeters. So that's 0.5 times 10 per minus 2. 0.5 times 10 per minus 2. If you calculate this with your calculator, you're going to have 1.13 times 10 per minus 5 farad. If you want to convert this to microfarad, that means your C equals to what? 0.113 microfarad. So don't convert it to microfarad. You want to leave it in farad. Now you have to also calculate. Sorry, this is not to epsilon naught. This is not the value for epsilon naught. I'm using this at mu naught. Is your mu naught, that is 4 pi times 10 per minus 7. That's your mu naught. Your epsilon naught is 8.854 times 10 per minus 12. That's the value of your epsilon naught, 8.854 times 10 per minus 12. So note this value of your epsilon naught. So this is not the value. Your epsilon naught is what? 8.85 times 8.854 times 10 per minus 12. So that's the value of your epsilon naught. So we are not going to use this. We're going to use 8.854 as 8.854 times 10 per minus 12. So if you recalculate this using your calculator, let me rub that off. If you calculate it using your calculator, you're going to get 7.97 times 10 per minus 9 farad. You can leave your answer like this or take it to nano. You know, your 10 per minus 9 means nano, so that's 7.97 nanofarad. So this is the capacitance of the capacitor. Now you have to calculate the total charge. Now, for you to calculate the total charge of the capacitor, we know that our Q is equal to what? CV. If you go back to from here, the charge of our capacitor is what? The capacitance times the voltage. If you make the charge solid formula, that means your Q is equal to what? Capacitance times voltage. So in this case, I will give me the capacitance. We already got the capacitance to be what? 7.97 times 10 per minus 9. So our C, our capacitance is what? 7.97 times 10 per minus 9 farad. Do you know our voltage? No, we are not giving our voltage, but we are giving our electric field. And from the formula from electric field here, we know that our electric field is what? Volt per distance. So that means our E, our electric field E, is your what? The voltage over distance. So what's the voltage? Make voltage substitution. That means our voltage is what? ED. E times D. So what's the electric field? The electric field is given as what? That's 3000 volts per meter. So that's 3000 times the distance. What's the distance? The distance is what? 0.5 times 10 per minus 2. That's times 0.5 times 10 per minus 2. If you calculate using a calculator, you're going to get the voltage to be equal to what? 15 volts. Then you can apply that here. Since you have your capacitance to be this, your voltage to be this. So you can calculate your charge. And what will be your charge? Your charge will be what? Capacitance. What's the capacitance? That's 7.97 times 10 per minus 9 times the voltage. What's the voltage? The voltage is what? 15 volts. If you calculate this using a calculator, your charge will be equals to what? This is 1.2 times 10 per minus 7 coulombs. If you convert it to microcoulombs, that means your charge will be equals to what? 0.12 microcoulombs. So this is the charge on the capacitor, and this is the capacitance of the capacitor. So you have to calculate the capacitance and the charge, and we've calculated that. Let's move to the next example. Example 2. We have to determine the potential difference across a 4 microfarad capacitor. So you are given the capacitance of the capacitor to be what? 4 microfarad. So your C is what? 4 microfarad. I know that your 1 micro is what? 10 per minus 6. So you're going to have about 4 times 10 per minus 6 farad. And you're given the charge on the capacitor, your Q, the charge to be what? 5 millicoulombs. 5 millicoulombs. I know your milli, as we said earlier, 1 milli is what? 1 milli is 10 per minus 3. So we convert this 5 millicoulombs, we're going to have what? 5 times 10 per minus 3 coulombs. So you have to calculate what? Determine the potential difference. You know that your capacitance is given as what? Q over V. So make the voltage, it's the formula, that means the voltage is what? Q over C. By making voltage the formula, and you are given the charge will be equals to what? So you are given the charge. What's the charge? That's 4 times 10 per minus 6. No, the charge is what? 5 times 10 per minus 3. The charge is 5 times 10 per minus 3. And you are given the capacitance. What's the capacitance? That's 4 times 10 per minus 6. 4 times 10 per minus 6. So we calculate this, your V, the voltage and the capacitance will be equals to what? 1250 voltage. So that's the voltage on the capacitor, that's the potential difference on the capacitor. Or if you convert it to kilovolts, that's 1.25 kilovolts. Now you have to find the charge on a 5 picofarad capacitor. So this is another question. A 5 picofarad. So you are given the capacitance to be what? 5 picofarad. And I told you that your 1 picofarad means what? 10 per minus 12. Your 1 picofarad is what? 10 per minus 12 farad. So 50 picofarad will give you what? 50 times 10 per minus 12 farad. If you convert it to farad, and you are given the voltage to be what? The potential difference applied to about 2 kilovolt. That means your V is what? 2 kilovolt, and your 1 kilo is what? 1000. Therefore your 2 kilovolt will be equals to what? 2000 volt. That's why 2 kilovolt is 2000 volts. And you have to calculate the charge Q from the capacitance of the capacitor. If you make charge from that means your charge will be equals to what? CV, the capacitance times voltage. And what's the capacitance? The capacitance is given as what? 50 times 10 per minus 12. 50 picofarad, which is 50 times 10 per minus 12. That's why you have this. Times the voltage. What's the voltage? The voltage is what? 2000. So 50 times 10 per minus 12 times 2000. If you calculate this, you're going to have 0.1 times 10 per minus 6 coulombs. So you convert it to 10 per minus 6 means what? Your 1 micro is what? 10 per minus 6. And if you convert this, I'm going to have 0.1 microcoulombs. So that's the charge on the capacitor. So let's move to the next example. A direct current 4 ampere. So that means the current is 4 ampere flows into a previously uncharged capacitor. So the capacitor was uncharged previously. And what is the capacitance of the capacitor? That's what? 20 microfarad. So that's 20 times 10 per minus 6 farad for 3 milliseconds. So the time it chooses to flow is what? 3 milliseconds. That's 3 times 10 per minus 3. Time is 3 milliseconds. That's 3 times 10 per minus 3. You have to determine the PD between the plates. You have to calculate the voltage between the plates. To know the voltage, you're going to use your V. Now your Q is what? CV. That's the charge on the capacitor. So that means your V now will be what? Q, the charge, over the capacitance. Are you giving the charge? No. But you can know your charge. Your Q equals to IT. Your charge is what? IT. That means your V is what? IT over C. Where your I is the current. And what's the current? The current is given as what? 4 ampere times the time. What's the time? The time is 3 milliseconds, which is 3 times 10 per minus 3. Then divided by the capacitance. What's the capacitance? The capacitance is 20 microfarad, which is 20 times 10 per minus 6. If you calculate this, you're going to get the voltage to be equal to what? 600 volts. So that's voltage between the plates. So your V equals to 600 volts. So let's move to the next example. A 5 microfarad capacitor is charged so that the PD between the plates is 800 volts. That means the capacitance C is 5 microfarad, and if you convert that, will be 5 times 10 per minus 6 farad, and the potential difference between the plates is given as 800 volts. That means the voltage, your PD is 800 volts. Calculate how long. So you're looking for time. How long? That means you're looking for the time. How long the capacitor can provide an average discharge current of 2 milliamp. That means the current is 2 milliamp. So current is 2 milliamp. If you convert this, that's 2 times 10 per minus 3 ampere. So if you use the formula, your Q equals to what? IT. So to get your time, that means you're going to have what? Q divided by I. I give me the current. Yes, I give me the current. I give me the charge. I don't give me the charge. But from your formula, your Q equals to what? CV. So substitute that into this. So that means your T now will be equals to what? Instead of Q, you're going to have CV, which is capacitance times voltage, over the current. What's the capacitance? The capacitance is given as what? 5 times 10 per minus 6. What's the voltage? Voltage is given as what? 800 volts. And what's the current? The current is given as this. So you can calculate that. That's, what's the C? That's 5 times 10 per minus 6. Times, what's the voltage? The voltage is 800 volts. 800. Then divided by, what's the current? The current is given as what? 2 times 10 per minus 3. 2 times 10 per minus 3. If you calculate this, you're going to get your time to be equal to what? 2 seconds. If you calculate it using a calculator, that means the time is what? 2 seconds. So this practice question, you have to go through them. Question number 1, 2, and 5. To go through this practice question, let's move to the next example. Now you have a ceramic capacitor has an effective plate area of 4 centimeters square. That means the area is what? 4 meters square. 4 centimeters square. Sorry, you convert that to meters square. That will be what? 4 times 10 per minus 4 meters square. You convert that. Separated by 0.1 millimeter of ceramic. So that means the parallel plate capacitor is separated by what? A dielectric, which is 0.11 millimeter. That means the distance between the parallel plate capacitor is what? 0.1 millimeter. If you convert that, you're going to have what? 0.1 times 10 per minus 3 meter. And you're given the relative permittivity to be 100. That means your ER, your epsilon R, relative permittivity is what? 100. Calculate the capacitance of the capacitor in picofarad. So you want to calculate the capacitance of the capacitor in pico. So your capacitance is given as epsilon naught, epsilon R, A over D. What's the epsilon naught? I said earlier, your epsilon naught is a constant, which is what? 8.854 times 10 per minus 12. So you have this. I give you your epsilon R, your relative permittivity to be 100. You are given the area, you are given the distance. So with that, calculate your capacitance. And what's that? Your C equals to what? What is epsilon naught? That's 8.854 times 10 per minus 12. Then times the epsilon R. And what is epsilon R? That's 100. Times the area of the plate. What's the area of the plate? That's 4 times 10 per minus 4 times 10 per minus 4. That's the area of the plate. Times 10 per minus 4. Then divided by the distance between the two plates. What's the distance between the two plates? That's the thickness of the dielectric material. And what's the distance? It's given as 0.1 millimeter, which is 0.1 times 10 per minus 3. 0.1 times 10 per minus 3. If you calculate this, the capacitance will be equals to, that will be 3.54 times 10 raised to the power minus 15. 3.54 times 10 to the power minus 15 farad, and you are asked to put it in what? In picofarad. So in picofarad, that will be 3.54. Now your pico is 10 to the power minus 12, so separate that. That's 10 to the power minus 3 times 10 to the power minus 12, because the combination of these two will give you 10 to the power minus 15. So that will be your C to be equals to what? 0.00354. That we return this to standard form, that's 0.0354. Then 10 to the power 12, that's picofarad. So that's your capacitance in picofarad. Now B, if the capacitor in part A, this capacitor is given a charge of 1.2 microcoulomb. So that means the charge of the capacitor is what? 1.2 microcoulombs, and that's equals to what? 1.2 times 10 to the power minus 6 coulombs. You have to calculate the voltage, the PD between the plates. So from your formula, your Q is equals to what? CV. So make V of the formula, that means your V is equals to what? Q over C. And what's your Q? Your Q is given as what? 1.2 times 10 to the power minus 6. And what's your charge? Your capacitance. Your capacitance is what? 3.54 times 10 to the power minus 15. 3.54 times 10 to the power minus 15. If you calculate this, your V will be equals to what? 1.2 divided by 3.54. That's 3.4 times 10 to the power minus times 10 to the power 8 voltage. So that's the potential difference between the plates. 3.8 times 10 to the power 8. So let's move to example 9. A parallel plate capacitor has 19 interleaved plates. So that means the number of plates is what? 19. So that's the number of plates. Each 75 mm by 75 mm. So that means the dimension of the plates, the number of plates is what? 19. The dimension is what? Dimension. The dimension of the plate is 75 mm by 75 mm. So we can know the area of the plate with this. What will be the area? The area of the plate will be equals to what? 75 times 75, because the area of this is a square. The area of a square is what? S square, and that's 75 times 75, and that's what? 75 times 75, that's 5625 millimeter square. So you convert that, you know, your 1 millimeter square, your 1 millimeter square is equals to what? 10 to the power minus 6 meter square. So if you have that, that means your area will be equals to what? 5625 times 10 to the power minus 6 meter square. So that's the area of the plate. Now it is separated by a mica sheet 0.2 millimeter thick. So it is separated by a mica sheet which is 0.2 millimeter thick. That means this mica sheet is a what? Is a dielectric material. That means the distance between the plates is what? 0.2 millimeter. So the distance between the plates, your distance between the plates is what? 0.2 millimeter. Then Assuming the relative permissivity of mica is 5, that means your epsilon r relative permissivity is what? 5. Calculate the capacitance of the capacitor. So to calculate the capacitance of the capacitor now, we know that our C equals to what? Epsilon naught epsilon r area over distance. But in this case we have n plates, so that means we are going to use our what? N minus 1. As I said earlier, we have n number of plates, so we are going to use n minus 1 for n number of plates. So that means your C now, because what's the epsilon? That's a constant with epsilon naught, which is 8.854 times 10 to the minus 12. So that means the epsilon naught is what? 8.854 times 10 to the minus 12 times, what's the epsilon r? Relative permissivity, which is 5 for mica, times what's the area? The area is 5625 times 10 to the minus 6, then times n minus 1 times what's your n? Your n is what? 19 plates. 19 minus 1, then divided by the distance. What's the distance between the plates? That's 0.2 millimeter. Let's convert that. 0.2 millimeter, that will be 0.2 times 10 to the minus 3 meter. That's 0.2 times 10 to the minus 3 meter. So that means the capacitance now, because to calculate this your calculator, you're going to have, so we calculate this, you're going to have 2.24 times 10 to the minus 8 farad. So you can leave your answer like this, or take it to microfarad or nanofarad. So let's take it to nanofarad. Your C equals to what? 0.224 times 10 to the minus 9. You are taking it to nanofarad. So that means your C equals to what? 0.224 nanofarad. So in nanofarad, you can also take it to microfarad. So let's move to the next example. Okay, practice questions. So you take note, this is your epsilon naught 8.854 times 10 to the minus 12 farad per meter.